Fans of space exploration have been inundated lately with articles about Elon Musk's plans to colonize Mars in the next 30 years, promising a glass-domed city of 1 million people by 2050, using fleets of starships to haul equipment and colonists to the Red Planet. We are going to examine Musk's own SpaceX demo slides and news releases about Starship, using very simple examples and mathematics to determine if the claims he makes about the ship are even possible. Since Musk first announced his plans to colonize Mars using a machine he called the ITS, he has constantly redesigned the ship into new variations, from the ITS to the BFS to the BFR to the current designation called Starship. But they are all similar designs: an upright cylindrical rocket that promises to land on foreign worlds on its tail, make its own fuel at that location, and relaunch from the surface and return to Earth. At 160 feet tall and 30 feet across, the Starship empty prototype shell Musk unveiled in Boca Chica towered over the crowd in attendance as Musk told them it would have a payload capacity of 100 metric tons, unlimited reusability, and room for 100 people at a time to facilitate Mars colonization. All we are going to do with simple math is demonstrate how the ship, as presently designed, is nowhere near capable of delivering on that promise. The SpaceX website provides basic information about the vehicle and dimensions, indicating this machine will be 30 feet across, or 9 meters. According to Musk's own presentation, Starship will have a central vertical access corridor to get from deck to deck. Although no dimension is given, for the purposes of this breakdown, we'll assume the corridor to be 8 feet across. So let's break this down. If the vehicle has a diameter of 30 feet, or 9 meters, then it would have a radius of half that, 15 feet, or 4.5 meters. The 8-foot wide corridor would have a radius of 4 feet, giving a crosscut of the machine a donut appearance. That donut of usable space would then be 11 feet wide. The outer perimeter of the craft would be approximately 94 feet, and the perimeter of the access corridor would be about 25 feet. The total area of that deck would be 705 feet, minus the 50 square feet of area for the corridor, leaving 655 square feet of space. Dividing that floor space into 8 berths, each unit would have about 81 square feet. These units would be 11 feet deep, 3 feet wide at the narrowest, and 12 foot wide at the widest. For comparison, this is smaller than an average-sized master bathroom. That berth, in this configuration, would have to fit 4 adults for the entire duration of the mission. However, Musk claims there will be 40 cabins instead of 24, spread across 3 decks. And that creates a problem. While you may have only to house 3 persons per berth now, that berth is now 30% smaller. Those compartments would also have a 2-foot wide access port, which is too small for most adults, especially if they're wearing bulky spacesuits. Now, maybe SpaceX can find 100 people that can live in those cramped conditions, who are traveling extremely light given the length of time they will be away from Earth, some of them for forever. One thing they will not be able to go without, however, on their journey is food. The advertised payload capacity of Starship on the SpaceX website is 100 metric tons, or 220,000 pounds. That is the weight allowance for everything from the oxygen tank bulkhead to the tip of the nose cone. So let's see if 100 tons is enough. We'll start with the weight of the 100 intrepid colonists. We'll assume the persons selected to go will be healthy, fit adults with an average weight of 200 pounds. Nice easy number of 20,000 pounds, or 10 tons, leaving 200,000 pounds of payload capacity. According to the website nasa.gov, astronauts aboard the ISS eat 3 very expensive meals per day, each weighing approximately 1.83 pounds. With 100 people eating 3 meals per day, weighing 1.83 pounds each, the expected transit expected to take up to 9 months, given the large size of the ship compared to Mars rover missions, they'll require 148,230 pounds of food. They'll also require water. Skimming available news releases, we find that every supply trip to the ISS brings 400 gallons of water with them to top up the tanks for a crew of 4. That the ISS has a water reserve of approximately 530 gallons, and that the ISS is able to reclaim only about 93% of the water they consume, even with the best technology. This is for a very small crew, and they recover 3.6 gallons of water per day per crew member. Which reaffirms this release from Pancopia that states that a 4-man ISS crew uses 12 gallons of water per day. If they recover 3.6 gallons per day per person, the 7% loss is 0.27 gallons per day for a crew of 4. Running through the equation for 100 crew on Starship on a 9-month voyage puts them at losing over 30 tons of water while en route. On top of that weight, the ISS has 530 gallons of water in reserve for 4 people on average on a station in low Earth orbit, keeping that ratio for 100 Starship crew, which will be unable to turn around and return to Earth. The Starship will require an additional 13,250 gallons. This is just for the human consumption. Any hydroponics lab would require extra water on top of this amount. Taking the total payload and deducting the weight of the crew, their food, and the water they require, assuming fresh supplies will be waiting for them when they arrive on Mars, the Starship is already 121,000 pounds short of payload capacity, and we haven't added anything else to the cabin yet. No clothes, books, computers, environmental systems, bridge controls, or exercise equipment. No beds, chairs, ladders, walls, or bulkheads. Not even the 280-pound spacesuits that each crew member will require. Just people, food, and water. In fact, the diagram flashed up at Musk's unveiling speeches has no reservoirs for fresh water, gray water, or black water visible. In the end, none of these calculations will likely need to be sorted out, since the machine itself has a built-in failure point that has escaped Musk and his engineers, and it's in the massive fuel tanks. Musk's demonstration slides for the tank design is rudimentary, of course, but shows a cylinder with convex ends holding the liquid oxygen. The aft end of that vessel extrudes into the tank holding pressurized methane gas. As a universal rule of thumb, heavy gauge pressurized vessels are cylindrical around their width, with rounded edges and no corners to minimize stress on any particular seam. The oxygen tank in Starship follows that guideline, but the methane tank does not. So when the tanks are at equal pressure, the methane is going to be forced into corners at the outside skin, trying to push its way out. If the methane tank is pressurized greater than the oxygen tank, it will want to buckle the dome under the pressure until both sides are equalized. Now it's true that the Saturn V rockets, amongst others, had a similar design, with a rounded cell inserted at the bottom of another pressure chamber. So how did they manage to pull this off? It comes down to the materials in the sidewalls. Modern ULA boosters are constructed from thick aluminum plates that are milled into a diamond or grilled lattice, which provides structural support. The base material of this outer skin is roughly the width of a human thumb. It is friction stir welded along the entire seam, producing a joint that is indistinguishable from either piece. In this giant cylinder, there are only 4 such seams, creating what is, in effect, one solid piece of aluminum tube. But this is what Starship is made out of, sheets of 301 stainless steel, the width of a dime. This ultra-thin material is stamped or cut into pieces and welded together, requiring thousands of seams to hold together these small sheets of thin material that is notoriously difficult to work with. Fewer seams, fewer problems. The Starship designs to date have not only been rudimentary, they have been remiss in so many details it's hard to count. Certainly the SpaceX engineers need a bit of a wake-up call, and other artists have been providing their own concepts in the meantime. Here's a few examples. Let's assume the crew has survived the 9-month trip to Mars without dying from radiation, starvation, thirst, or being murdered by their very cramped bunkmates. Starship lands on the surface of Mars. All they have to do is exit the craft. But where's the hatch? There it is, about 10 stories off the ground. But that can't be right. Surely they're planning on something a little closer to the surface? Nope. There it is, 100 feet in the air, and you're meant to get to the surface by means of a cable crane. And that is consistent with the basic design. To get to ground level in the ship, crews would have to go through the pressurized propellant tanks, so they can't get there from the payload compartment. You know what else crew can't get to? The engine compartment. Any engine failure en route means Scotty is going to have to suit up for an EVA. And just to confirm, yes, the airlock is designed into the second lowest level of the pressurized area. It has direct access to the central vertical corridor of the ship, which may work fine when the vehicle is in space and not subject to gravity, but when the crew are climbing aboard on Earth and debarking on Mars, They will not be able to float between decks, and there doesn't seem to be an elevator in this diagram, or even a ladder. Considering they will all be wearing bulky 280-pound spacesuits on and off this craft at either end, this would seem to be a major oversight. Musk revealed to the world on Twitter that the purpose of the giant atrium windows in the nose cone of Starship would be used for travelers to enjoy concerts. And what a backdrop it would be. Unfortunately for Musk, the giant sunlight will only ever be science fiction. Space windows are damned heavy and incredibly expensive. Largest window in space at present is the cupola on the ISS. And the reinforced construction, plus reinforced shutters for its protection, bear no resemblance to the 30-foot tall, 40-foot wide atrium windows shown by Musk. The cupola assembly is only 5 foot tall, under 10 feet across, with the center window 2.5 feet wide. Cost of this feature, plus the module it's attached to, was $409 million to build, and at $10,000 a pound, cost about $40 million to launch, since it weighs 2 tons. Next failure of Starship, on top of the cabins and the galley, there is also supposed to be a specialized solar storm shelter for its 100 crew. And this is what 100 crew would look like in that shelter, stuffed in and standing up. It would require an entire deck that had nothing else on or in it. These 100 crew icons are to scale at 2 feet wide and 1 foot thick. Considering that no one in the room has showered since they left Earth, and they will never have another shower until they return, deodorant will definitely be a key commodity, and this station would be ridiculously uncomfortable. Our conclusion is that Starship falls well short of being able to accommodate 100 crew in any regard, which is consistent with NASA recommendations regarding required volume per crew member. In 2013, NASA's Human Research Program issued a report stating their recommended minimum net habitable volume per crew member. Their team compared other space stations and the volume per crew member before coming up with their absolute minimum of 25 cubic meters per person, well below any other former craft. According to the SpaceX presentation, Starship has 825 cubic meters of pressurized cabin, which may be more than an A380 cabin. But, according to NASA findings, this is only enough space for a maximum of 17 crew, 83 short of the promised 100. Episode 2 of this series will go into much more detail about what the crew will require to survive the transit to Mars and the rest of the facilities they will need to build into Starship that, to date, appear to have gone unrecognized. Thank you for watching this pilot presentation of the Common Sense Skeptic. Be sure to subscribe to this brand new channel for future upcoming content.